So how are you guys doing today? Doing good? Perfect. You guys at lunch? Perfect, good. Because I'm full too. Let's go start the chapter 1 again. So we start doing a chapter 1 and 2 and 3 once more because I actually want to tell you what type of question you will see on the exam and the quiz, almost like a similar format. So you'll be better prepared for the exam, which we're gonna have sometime soon. So we're in a Friday pod, I believe, so it'll be 19th of February. So we still have quite a time, 2 weeks, but let's start with this actual practical problem solving, okay? So in chapter 1, one of the kind of mathematical problem we're gonna try is unit conversion. So if you want to do unit conversion, we normally do that with the density. So if you guys remember this one, density, this will actually tell you how heavy your subject, your sample is over some unit volume. So it will tell you density of something by just expressing how heavy the mass number over the volume. So you can tell what the density of the sample you have just using density information there. So obviously, most of the time we're going to use gram or kilograms or pounds and so on. A lot of numbers for mass units. Volume you can use a centimeter cube, meter cube, and so on. We have a lot of things too over here, or liter, and so on. So, for example, if we have 1 gram per centimeter cube, we use this number quite often because this is density of water. So we're actually going to use this number a lot, but this is the same as 1 gram per milliliter. So the mil is just meaning milliliter. So you know what 1 liter is, right? So 1 gallon, I think is about 3.454 liter or something. But the milliliter simply means 1/1000th of something. So 1 mil is 1/1000th liter. Okay. So that is this much. It's like a 1 centimeter, 1 centimeter, 1 centimeter, 1 centimeter cubic structure. This is how much that 1 mil is, or 1 centimeter cube. They mean actually the same thing because they experience the same volume. Okay. So anyway, if that is the case, the one we tried before was we tried to convert this density unit to kilogram per liter, okay, which is also quite common in more macro scale subject. So let's try to do it in this way. So if you want to try to do this, maybe I'll try to put, instead of 1 at this time, I'm going to put 1.0, okay, 1.0 here. So we're going to do the unit conversion from here. So this is the same as 1.0 gram over centimeter cube, right? Okay, and we're going to make a table. So when you try to do the unit conversion, you need to have conversion factor. So you need to know how long they compare to the other units and everything. So I'll give you the conversion factor, don't worry about it. So we're gonna change this one to kilogram to meter cube. So kilogram, 1 kilogram is equal to 1,000 grams. So whenever you try to change this unit to kilogram, you need to put the same unit top and bottom. So whenever you make the table using this conversion factor, you just put the numbers in here, top and bottom. But you have a unit to be replaced by on the top. So you're gonna keep this number, 1,000 grams, at the bottom. So that way your units for the mass will be canceled, top and bottom. Okay? And then I'm gonna copy this number on the top. So in that way, now you convert your mass unit to kilogram now. Okay? So that is done. And then we're gonna change now. So here you have a kilogram per centimeter cube now. But we also want this to be in this new unit for volume. So I'm gonna also give you this type of conversion factor over here. So I'm gonna copy this one on the top now because you have a volume unit at the bottom now. So to same unit to be canceled, it has to be on the top instead now. So we'll put 100 centimeter, and I'm gonna put the 1 meter at the bottom. Okay, and then the thing is, as you know, the volume itself actually means like a 3D structure, 3D area. So that's why it has to be cubed. It has to be multiplied by 3 factors. So we'll also do cube on both top and bottom. So if you cube those 100 centimeter and 1 meter cube together, then you'll see 100 centimeter cube, okay, here, and then is 1 meter cube, okay? Because you have to cube both of the factor in the parentheses. So you're gonna do 1 million centimeter cube over 1 cube is just 1 meter cube, okay? So if that is the case, you're done here. Only thing you have to do is you cancel those 2 now, right? So only thing you have to do is the 1 times the 10. And then divide by 1. So you have 1,000 over here at the bottom. So if you see the numbers on the bottom of the table, meaning you're gonna divide it, okay, by that number. If you have numbers on the top, meaning you're gonna multiply it, okay? But the number you started with is 1. So, but you have a 1 times 1 is still 1, right? 1 times 1 is still 1, but over 1,000. So you're gonna divide this number by 1,000, multiply 1, still is 1, okay? And then here, this will be divided by 1, so it'll be still 1, but will be multiplied by a million. So simply, if you have a numbers on the top, just multiply. If you have a numbers in the bottom, just divide that number by. Okay. So if you do this one, it's simply 1,000 kilogram per meter cube. So if you have a 1,000 kilogram per meter cube, means the 1 gram per centimeter cube, meaning they are same in density. Same density. Just a different number because you changed the units there for the density. Okay. So if I give you some numbers like this, you can have a unit conversion done, so you can have an answer for it. You can try. Okay, so let's try one for ourselves today. So if I give you 20,000 kilogram per meter cube, I want you to change this one to gram per centimeter cube. So you're going backward now. Can you guys do this maybe 3 minutes? You can try this one now. But we'll do this together anyways. But I want you to try at least once. So you're actually doing the other way. Only thing you have to know is the conversion factor. Okay. That's it. Okay. Try to use the conversion factor to get your density unit converted to the new units for density. Okay. So try to make a table and try to put the conversion factor numbers top and bottom so you can cancel the same unit on top and bottom, and then you can get a new unit for mass and the volume. So it will be unit for the density. yeah, it will take some time. I think normally it takes about 3 minutes. If you practice quite a time, and you can normally get this through all steps in 3 minutes, I believe. And yeah, you can also use the calculator on the exam, but make sure you guys have a really like a small and cheap calculator. Do not bring like what's, I don't know, the calculus, some weird function. Yeah, don't do that. Alrighty, so let's do this together. So once again, this is the same as 20,000 kilogram over 1 meter cube, right? So I wanna convert this unit first. So I'm gonna copy 1 kilogram at the bottom to get those two units canceled, and then I'm gonna put 1,000 grams on the top, so you can switch to the gram now, because you have the same unit cancel on top and bottom. You got a new unit for the mass now. So we're done with the mass unit, but we're gonna change that volume unit so we can get a new density units there. So I'm gonna just do it the other way. So I'm gonna put the 1 meter on the top at this time, because we're gonna do it the backward now, and also we're gonna put 100 centimeter at the bottom at this time. Okay, because we're going the other way than we did before. So then once again, you're gonna cube those top and bottom ones, and then you're gonna have eventually 1, because 1 cube is still 1, but mirror cube, which now you have a unit cube, and then it's 1 million centimeter cube over here. So in this case, you're going to have 20,000 multiplied by 1,000 divided by 1, and multiplied by 1 and divided by million. Okay, so that means you have a 20,000 divided by 1 times by 1,000, and also divide by 1 million. Yeah. So if you do that, that will be right this one. So simply you dividing 20,000 by 1,000. Okay. So that will be 20. Okay. Makes sense, right? Do you want to do one more time, or can I move on? Just one more time, maybe? Sure. Just one more, yeah, just do one more time. So how about can you guys do 0.75 grams per centimeter? Sometimes I will give you on the exam gram per mil. Just remember though, it's the same thing, okay? So same. And I want to switch to now kilogram per meter. Okay. And then okay, I'll give you 3 minutes again. Check this one again to 100% sure that we know how to do this on the table. I know you guys already are capable of doing this somehow now, but we can be more certain on those by just practicing a lot more. Okay, maybe 2 more minutes. Just try to make a table and try to get the same old unit top and bottom so it be canceled, and switch to the new unit. And then you got the number just by the ones on the top multiplication, the ones on the bottom just division. That's it. Right, just 1 more minute and we'll do this together. Okay, so let's do this together real quick. So this is the same as what? 0.75 grams over centimeter cube. So I'm gonna make a table. And I'm also going to use the this one again, but now we're gonna switch the gram to kilogram. So I'm gonna put 1,000 gram at the bottom, and I'm gonna put 1 kilogram at the top. So those two can be cancelled to to be a new unit kilogram. And now we'll put the 100 centimeter, 1 meter, okay, and just cube, because this is actually the length conversion factor. That's why we're cubing the length unit to be unit for volume. So you have a cube this one, so the 1 million again, centimeter cube, and this is still 1, but meter cube over here. Okay? So if you do that all, so simply this is the same as 0.75 times by 1, but divided by 1,000. And also multiply that number by a million, and also divide by 1. So if you do this one, you're going to have 750 kilogram per meter cube. Okay. So here's the thing. Do you see those numbers in here? And I have a question about the chapter 1 again. How many sig figs are here? 2. 2, perfect, good. How many sig figs are here? Okay, so this is 1.0. Same as 1, but I put not just 1, but 1.0, because there are 2 sig figs there. You guys remember this? Okay, 2 sig figs. Same here. I put 1.0, not just 1, because I wanted to do 2 sig figs here. I did it intentionally. So if you have this number here, how many sig figs do you have? 2, perfect. Because you're going to follow the least numbers of sig figs when you do multiplication or division, right? You guys remember this? Okay. So if you put this, so if you just have this number right here, you don't know actually how many sig figs are. It could be 2 at least, but it could be 3. We don't know yet. But if you look at the calculation work, because the least number of the sig figs is 2 here. So we know for sure now, looking at the calculation work, there's 2 sig figs, not 3. Okay? It's because of their information over there. So if I wanted to put this in scientific notation, do you guys remember this scientific notations? So if you want to put this in the scientific notation, it should be 7.5 times 10 to second. Okay. If you do 7.50 times 10 to second, that'll be wrong. Because you know about this calculation work. There were 2 sig figs, which you can follow the least numbers of sig figs, which are 2. So you can only do 2 on your scientific notation to express the same number in this form. Okay? Makes sense, right? Okay, good. Alrighty. Alright, so we can do another one. So if I show you this one, okay. This is what we did before so many times. Right here. And then I'll give you, so this is a carbon ion, this is 12 grams per mole. This is 4 is 16 grams per mole. And this is 16, but they're diatomic molecules, so it's 32 grams per mole. So if we have 16 grams of methane, if we have 32 grams of oxygen gas molecule, they're all going to make 100% full chemical reaction, because you have, oh, no, sorry, not here. You need to balance first. So it'll be 1, that'll be 2, so it'll be 2, okay? So instead of 32, you need to have a 64, okay? So if you have a 64 grams of the oxygen gas molecule, meaning you have 2 moles of O2. Because once again, your formula weight, molecular weight of the O2, because they're diatomic molecule, not just one, but there are 2 oxygen in one molecule. So that makes 16 times 2 makes 32. So 32 grams per mole is formula weight, molecular weight. And so if you try to divide the actual mass by molecular weight here, you get the number in moles. So the mole simply means how many in very big number, which is Avogadro number. You guys remember this? Yeah, go ahead.
Can you explain like where you got the first, like in the big circle right under the bill? Can you explain where you got those first couple numbers that you?
The 16 and 32, right? Yeah, perfect. So this is I totally made up. Just kidding. This is on the number you see on the periodic table. That was a bad one, right? So anyway, so the periodic table will be given. So meaning you will be able to know what is the atomic mass of each different chemical elements. So if you look at the oxygen in the periodic table, you see like a 15.99 something. Yeah, 99 something over there. And then we just grab that number to multiply by 2 because the oxygen is so oxygen gas molecule. That's actually a very good question, I think. Very good question. Because this is going to be diatomic molecule. So I briefly mentioned before at the beginning of the semester. So diatomic means there will be 2 atoms of the oxygen will bond together to be one molecule. So we call this diatomic molecule. You don't have to know why it forms a diatomic molecule. But if I have to explain, it's this one. You know, have you ever seen the movie? It's animation movie named The Bee, like Honeybee. Have you watched that movie? No? So it's the movie about some honeybee, but it's animation, right? So actually the bee can talk to human. Yeah. Oh, yeah, right, perfect. Oh, good. Oh, you guys, some of you watched it, really. Oh, that's the first time I'm finding people watch that movie. So if you have one scene, I want to explain to you that kind of explains why, somewhat, because the human talking to the honeybee, and then the human was curious about that. You know, the honeybee has wings, right? And the human was like, oh, I'm so jealous of you, because if I have wings, I'll be flying all the time. And why aren't you flying all the time, right? Because I have wings. And then you know what honeybee said? Honeybee said, you're human, you have legs. Why aren't you running all the time? Because it's tiring. Even though you have a wing, you can't fly all the time because it's tiring more to just fly all the time. So same here. If oxygen become alone here, later we're gonna learn about the octet rule, they become really, really unstable. So they need to grab somebody. They need to grab somebody to be more stabilized. Meaning they don't have to be like excited all the time. They can be always held by something else, which is maybe diatomic molecule. So they can be bound together. So think about it. If you're just running and you find somebody and just grab them together, then you can move slower. You're heavier now and you're more bonded to the other one. It also gives us pretty good bonding there. Then you'll be less moving. In chemistry, we call this kinetically more stable. They were moving much slower. So in that case, they always try to be in a lower energy level, which they can be more stabilized. Which, like we as a human, we always want to lay down on the couch and enjoy the time. So it's pretty much the same thing. But it is technically because it's diatomic molecule. So they can be bound together, so they can be more stable. So they would love to bind other ones, so it makes O2, not just O. Okay? So that's why we multiply this 16 by 2. So then you have one molecule that weighs about 32 grams if there's 1 mole of that molecule. So the 1 mole is equal to 6.022 times 10 to 23rd. So it's a huge number. We use this number because the actual mass of the proton or neutron is very small. Okay, so you can count them all, but just multiply that by a huge number, so you can use very nice and simple integer number that is a mole. So if you do that, that just becomes just 16. So 16 is atomic mass of the oxygen, and multiply by 2 to make one molecular weight of a molecule, so that'll be 32. So meaning, think about it. If you have O2, this is a molecule, that 32 grams per mole simply means if this one is 1 mole, that will weigh about 32 grams. That's what it means. But then if you have a 2 moles, twice much of what you had before in 1 mole, that means it will weigh about obviously double amount of weight too. Because you have a twice much numbers of that, and then you have a twice much heavier weight on it too. Makes sense, right? So that actually tell you if you go the other way, meaning if you have maybe 96 grams, for example, I just know, oh, that has to be 3 moles of O2. Because I know how much it weighs in 1 mole. It's just triple of that. So it gotta be 3 moles. That is why if you try to divide the actual mass, which is 64 grams, by your molecular weight, you can actually tell how many moles of O2 you have right there, which is 2. Makes sense, right? Okay, good. So if that is the case, once we're done with the balancing the chemical equation here, we know 1 methane will interact with the 2, in this case, which is perfect for this one. You have 1 mole, same here, 16 grams of methane, which is CH4 methane, over 16 grams per mole. Okay, so that makes, now we know, oh, if there's 1 mole of methane, it gotta weigh about 16 grams, but we do have a 16 gram, then it should be just 1 mole of CH4. So we have a 1 mole, 2 moles of O2, which is perfect for your molar ratio, which is 1 methane goes in, interact with the 2, that makes the 4 reactions. That is good for this one because we have 1 moles of CH4, we have 2 moles of O2, so it is also 1, 2. So it's a perfect full 100% interaction there. Okay, makes sense, right? So if I give you this equation, and I'm telling you, you have 16 grams of methane here, interacting with 64 grams of O2, which is a perfect ratio, perfect. There's no limiting, there's no abundant one at all. They're all going to be they're all going to be used up to make the product, which is what? Carbon dioxide and water. And then this total mass of the 2 products will be simply what? These 2. Because this is all used up, and if you just add 2 numbers together, there will be 80 grams, right? 80 grams. So the carbon dioxide and water formed after these 2 combustion reactions has to be 80 grams because we follow what? Mass conservation rule. Okay? Because the nothing cannot just disappear, or new thing just came from nothing for no reason is impossible in chemistry. It has to be same on lab reactants and the product side equal. It only changing their chemical composition or chemical structure. So they become a new product, but it doesn't mean you're going to miss any part of the carbon or hydrogen, oxygen. It's just all there, but in different way now. So you're making new products by just rearranging those elements in a new type of bonds there. Okay? So that makes sense now. If it's 400 reactions, no limiting reagents or no abundant one, that's going to be same mass left and right, right? Then it is done by mass conservation rule. That's we follow. Nothing just can't just disappear, just coming from nowhere. No, we don't believe that. That's not a science. Okay, so if I give you this example on the exam, I'll give you several rules, like a mass conservation rule, chemical element proportion rule, or other ideal gas, or any other rules, and you need to pick this one as your answer. Because that will make sense that some of these 2 grams, if it was 100% chemical reaction, has to be same on the other side in mass, by mass. Okay? Because you didn't lose anything. Makes sense, right? So in this case, if I give you this, I'll probably give you this for sure actually. I choose this unit out of 4 different choice. Multiple choice, you choose this one. Okay. Alright, let's go. So then there's one more thing about I may put on the exam is the atomic model, or this one. Okay, so if you have atoms, this is the nucleus at the center of the atoms. You have electrons moving around. Okay, over here. Oh, sorry, maybe the center is right here. So we have some protons and neutrons are kind of like a center around a center at the atom. So you have a nucleus on here, and you have electrons moving around it here. One thing I normally put for this one is the 99.999% of your atom is just simply empty space. This I normally do all the time in the exam. So I hope you guys remember this one. So the atom is not 100% fully filled with something else, but it's just vacant empty space. Other than just the very small, tiny, like subatomic particle combination at the center of the nucleus and the electron over here. They're so small. Like I mentioned before, if I am the nucleus, the electrons are moving like in the outside and at the edge of the Troy city. Since that's how much vacant or empty your atom is. So if I give you a dramatic example here is, can you guys hold your hand like this? Okay, like this, and then now you're feeling by touching your both hands together, you're now feeling that you're touching, your both hands are touching each other, right? But if you think about this one, technically your hands are not touching each other. So what might be the biggest building in Troy? I don't know actually. But if you choose the biggest building in New York City, which would be a huge building, right? Skyscraper. If you try to remove all this empty space in that building shrink down to 1 rice grain. Very small. So other than that, the building is just empty space. It's hard to believe because we are truly like a macro scale being. So it is really hard for us to understand how small the atom and how vacant the atom is. So whenever you're holding your hands together like this, what really happens to these two is actually electronic repulsion that the atoms will do with these electrons here and the protons. But they're so small, you cannot feel it, and you can even not see it because this is something you're gonna do next month. But do you know what the light is? Light. Light is the electromagnetic radiation, meaning if you don't have a light, you cannot see anything because you see something when your optical sensory organs catch the light deflected by some object. So this is green, right? This is purple. This is green because this subject deflect the light at the green wavelengths to my eyeballs. So it's kind of ironically saying this seems green to me because this one doesn't like the green light. So we get the green light from here. So we looked at as green objects. Isn't it kind of funny? Anyway, so we see this from the light, but this one is too small to be catched by our optical sensory organs where we interpret the light from the outside. in your mind. So that is why. Okay. Kind of makes sense. So, okay. I'll move on. All right. So there'll be some conceptual factual problems. Actually, we're gonna discuss more on Monday. But let's do just one more mathematical problems, and then we'll finish here. So if we have, if I give you, maybe this might be one of the hardest question again, which is limiting range. But I will give you maybe this one at this time. If we have a C5H12, okay, it is going through combustion reaction here. And then at this time, it will not be 100% full reaction because I'm going to make one of them as a limiting region over here. So this is the one. You can always assume that it will be carbon dioxide and water. Okay, and then what you can do is I'm going to give you some numbers in grams on those two. Okay, those two, and then I'm going to find out how many grams of these two products will be produced. Okay? So in this case, it will not be 100% because one of the reactants will be limiting agent, reagent. So you have 72 grams of here. We try to get the molecular weight of this one real quick, which is 5 carbons in one molecule here. So 5 times 12. It's right under the carbon. So carbon is 12. So 12 times 5 is 60. And you have a hydrogen which is about 1. So 1 times 12 is 12. So 72 grams per mole. Okay? So that is the molecular weight of this organic compound. And we're going to divide this actual mass again by 72 grams per mole. And unify there 1 mole of C5H12, which is actually pentane, but you don't have to know now. But this one. And here, you're going to have 32 grams per mole. So you have 2 moles of O2. Okay. So now you have one moles of pentane. You have 2 moles of oxygen here, and then you have to balance the equation first. So it'll be 5 carbons in one molecule. So minimum number you can try here for coefficient is 5. You can't get any lower than that. Because even though you try 1 over here, it carries 5 carbon already in one molecule. Then this carbon dioxide only has 1 carbon in it. So the least number you can try here is 5. Okay, so this is the minimum you can try. And then for here, you have a 12 hydrogen in one molecule. So water, luckily it has 2 for 1, so you can have a 6 that makes 12 hydrogen in it too on this side. So if you do this one, you have a 6 times 1 oxygen here. So you have in 6 water molecules, you have 6 oxygen atoms in it. You have a 5, there's 10, perfect, 10 oxygens there too. So here in total, you have a 16 oxygen on the right side of the chemical equation here. So to make the same number of the oxygen in here, it has to be 8, because 8 times 2 is 16. Okay, so now you find out, oh, I find out the stoichiometry now. If you have the pentane over here, they need to have 8 oxygen, but you only have 2. Here's the thing. So you have a 1 mole. You have 1 mole of pentane. Okay. Then you comparing this one to here, this one, right? So and then you can use the coefficient number here, which is 8, 1. So you're comparing this one to here, so it'll be 8 over 1. So you multiply 1 mole by 8 over 1, that is 8 moles. This is the amount of the moles of O2 you need to have 100% chemical reactions. So you need to have 8 moles of O2 because it's a 1 to 8 ratio. You have 1 mole, you have to have 8, but you only have 2. Meaning, this is our limiting reagent, which means 2 moles of O2 will be all used up. But this will not. This will not. So this is what we call abundant reactants, or you can say X. excess reactants here. Okay? So you have too many more, too much more. So not 1 mole of this one will not used up. Only a fraction of it will be used up. So then you only need to use the one that will be all used up, because we know there will be 2 moles of O2 will be all used up. And then think about it. If there's 8 comes in, there'll be 5 carbon dioxide and 6. And you know there'll be 2 moles of O2 will be all used up. Then you know there'll be 2 moles, and you go from here to here, right? So it'll be 5 over 8. Okay. And this is here to here, right? It will be 2 moles of 6 over 8. Okay, which is I think is 3 over 4. So then this will become 10 over 8. This will become 10 over 8, which is I think 1.25. And this will become 6 over 4, okay, which is 1.33333 moles. Okay. So meaning you're going to have a 1.25 moles of carbon dioxide. You're going to have a 1.3333 moles of water. Okay? And then only thing you have to do is multiply the numbers of moles by its molecular weight, which is 44 grams per mole. And this is 18 grams per mole. So the CO2 has 44 grams per mole because it's a 1 carbon 12, 2 16 with 32. The 12 plus 32 is 44. So 1 carbon dioxide will weigh about 44 grams. Water, 2 hydrogen will be 2. 1 oxygen is 16. So 2 plus 16 is 18, right? So if you multiply this number by 44, this number by 18, you get the final answer here and here in grams. So you know now how many grams of these two will be produced. So this is another example we tried so many times in limiting reagent related stoichiometry problems. Okay? So I'll stop here. We'll try to do this more.